Okay, let's talk about Transformers 2. This is the second lesson on Transformers. If you didn't watch lesson 24, please go watch it first, otherwise this probably won't make a ton of sense. But just a review on Transformers, we have a transformer which is two inductors that are put side by side. And remember that these lines of flux, whenever I send a current through this primary windings, we'll call it I primary. When I send it through the windings, we create lines of flux, of magnetic flux. And when those lines of magnetic flux are changing across this coil on the right side, it sends out an I secondary, right? And it acts like a source on the right side. And on the left side, it acts like a load. This inductor acts like a load. This right side acts like a source, providing power, providing current to the right side of everything else going beyond that. And we have a V primary across these primary windings, and we have a V secondary across the secondary windings. And what is being transformed is based off the number of coils in primary to the number of coils in secondary, made up with this turns ratio A, right? And so the ratio, if it was 2, then it would look like 2 to 1. 2 to 1 would be a step down transformer. Down here, if I said 1 to 20 across some transformer, well, this would be a step up transformer. And it would go from a lower voltage up to a higher voltage. So that's just dealing with the voltages and the currents. But now to this idea right here saying that it acts like a load. Well, if I wanted to do the Z, I can model everything on the right side of the equation with what we call the reflected impedance. And so everything inside my red box that they have inside of yellow can be modeled as an equivalent into this right here. And so if this was my load from the perspective of the primary side of the circuit, it can be simplified to look like this load right here. And so we do that with this equation. Z primary reflected is how it says on the equation sheet. It means the reflected impedance, and it simplifies to this right here. And so that reflected impedance, from the perspective of the primary side of the circuit, it can't tell whether there's a transformer there with everything else past it, or whether there's just this simple box with some Z amount. So that is called the reflected impedance. So the rest of this part is just describing some of the applications of transformers. Note that if I had, say, 120 volts to 0 on this side, and that was my V primary, well then using this same coil, and I just send the current through the I primary on this side, I can transmit across this transformer multiple different voltages. And so I could send an output wire here and a ground wire here, and that would have a turns ratio of 4 to 1, 120 volts, 30 volts on the other side. At the same time, with the same exact set of coils, I can just tap it. I tap a wire inside that coil, and now I have a 10 volt potential difference across the V secondary, and that one would have a 12 to 1 ratio. So with one magnetic field, I can generate multiple currents that are going to then flow out of these wires and multiple voltages that are going to be across them. That's a practical application. And as we talked about in class, we use transformers all the time, specifically for transmission systems. And so here's just a typical panel. It looks maybe a little bit crazy, but we have this high voltage, 700, 7200, and then it's going to go down to 240 across both of these, right? We have 120 here and 120 here, and that's pretty typical. So this would be a step down transformer going from 7200 volts down to 240 that we've tapped into by tapping this wire in the middle of the transformer. And if I wanted, I could use all 240 volts by going all the way across it. Say an elevator. The elevator would use all 240 volts, but the lights would just use 120 volts. On the other side of this, what's not showing is that imagine that this is like my high power, high voltage lines. And we talked about this in class, and I imagine, all of these wires up in the air going through. And then I can put a transformer on the other side that's a step up. and that's coming from my power plant. You know, burning coal, maybe if you're in California, you got some wind energy going, but we have a generator plant that is then transforming up, going out in these high voltage lines, and then it's going to a distribution transformer in, say, my neighborhood, or to Bancroft Hall, or another building that is going to use single phase 120 volts. Okay, so power distribution with step up and step down transformers, that's the primary use of transformers, but the other one that we can do is whenever we want to achieve maximum power transfer. And if we recall from Thevenin, right, from the Thevenin equivalent circuit, that if I wanted to achieve maximum power, I need my Z load, that's my Thevenin load, to equal my Z Thevenin complex conjugate. What do I mean by that? Here's my Thevenin equivalent circuit with a Z Thevenin and an E Thevenin. And then I have my Thevenin load, Z load. And so if I wanted to achieve maximum power in the circuit, then I need to adjust this, right? I need to change this. Well, if I have a transformer, then what I can do is I can treat it like a Thevenin equivalent, and I can make my reflected impedance Z primary reflected like the Thevenin load. And if I treat it as the Thevenin load, then I'm going to set it equal to the complex conjugate of Z Thevenin. So let's just practice with reflected impedance before we try to achieve max power.